So hello everyone, our team name is IBOG, and today we're talking about the automatic classification of Pubmed articles by cancer types using machine learning. Uh, our group consists of Dawatira, Samay Wazir, myself Ingo, and Dulko. So first of all, in this project, the top 10 cancer types in men were selected as the focus of the machine learning classification task. The choice to focus on men were motivated by the fact that cancer incidence and distribution differ significantly between sexes due to biological, behavioral, and lifestyle factors. Developing a sex-specific model allows for more meaningful patterns to be learned from biomolecular text and avoid mixing cancers that are highly gender-specific, such as prostate and cervical cancer. So the typical cancer included in the top 10 cancer types for men are lung cancer, prostate cancer, colorectal cancer, liver cancer, stomach cancer, bladder cancer, esophageal cancer, pancreatic cancer, kidney cancer, and last of all, leukemia. So to classify a PubMed article into cancer types based on textual features, several well-established supervised machine learning classifiers were employed. These algorithms are widely used in text mining and biomolecular language natural language processing due to their high effectiveness in handling high-dimensional features such as TF/ID vectors. So first of all is logistic regression. Logistic regression is a linear probabilistic classifier that estimates class membership using a logistic slash sigmoid function. Despite the simplicity, it performs exceptionally well for text classification tasks with sparse and high-dimensional data. Its ability to output class probabilities also makes it impenetrable and suitable for medical text analysis. So based on that fact, that's why we chose logistical regression as our classifiers in our code. We'll get to that more on that later. Next is support vector machine. Support vector machine is aimed to find the optimized superplane that maximizes the margin between different classes. SVMs are particularly efficient for text classification because they can handle high-dimensional feature spaces efficiently and robust to overfitting. Next one is the naive-based. Naive-based classifiers are a probabilistic data model based on the Bayes theorem of the assumption of feature independence. Despite this strong assumption, naive Bayes performs remarkably well in document classification and is computationally efficient for large text data sets. K-nearest neighbors. The K-nearest neighbors algorithm is a non-parametric instance-based classifier that assigns a class based on the majority vote of the nearest neighbors in feature space. While simple, KNN can be effective when sufficient training data is available, though it's computationally expensive for more larger data sets. Next one you have is random forest. Random forest is an assembly learning method that constructs multiple decision trees and combines their outputs to improve classification accuracy. It reduces overfitting and can capture complex feature interaction, making it useful for multi-class classification problems. So the next we have here dataset descriptions. The dataset contains PubMed with the following field: PUMID or PubMed identification, DP, date of publication, TI, title of article, AB for abstract of the article, type for the article type, or review clinical or trial. Cancer types is for target label, such as bladder, colorectal, kidney, or leukemia. So furthermore, title and abstract were combined to create a comprehensive text representation for each article. The cancer type column serves as a target variable for classification. So first of all, what we used was text processing. Before we turn to, we should know what text normalization is. Text normalization is the process that transferring raw textual data into a standard consistent format before it's analyzed by a machine learning model. Natural language processing models, raw text often contains inconsistencies such as uppercase and lowercase variations, punctuations, numbers, irrelevant words. Text normalization reduces this variability so that systematically identical terms are treated as the same feature. So the common text normalization setups include converting text to lowercase, removing punctuation and special characters, removing stop words such as the, and, or, is, or, tokenization, clearing text into words or phrases, and stemming or limmatization, reducing words to their base form. So first of all, we processed our text. Missing tiles or abstract were filled with empty strings. Tiles and abstract were considered a single text field. Text normalization, tokenization, a stop and removal applied using TF/IDF vectorization. Second is feature extraction. TF/IDF vectorization was used to convert text into numerical feature vectors. N-grams, unigrams, and bigrams were included to capture contextual word patterns. Maximum feature limit was set up to 50,000 to ensure memory efficiency. Next was the mode selection. As we thought before, logistic regression was chosen as a linear classifier of sparse high-dimensional data. The model was trained using L2 regularization with the Saga solver for computational efficiency. And fourth of all, and next, the data set was split into 67% training and 33% testing. 5-fold cross-validation was performed on the training set. Performable metrics included accuracy, precision, recall. F1 score, confusion metrics, probability estimates were also generated for each class. So, for the result, logistic regression. For our results, the logistic regression classifier achieved a high cross-validation accuracy, indicating a good generalization. Test set evaluation confirmed that the model accurately classifies Pubmed articles into respective cancer types. Third, the confusion matrix shows that the model correctly distinguishes between classes with minimal misclassification. So example prediction for a new article should be like, input should be, this study investigated early stage method for colorectal cancer. It should come out as predicted class colorectal cancer class probability. So it should be something like bladder is 0.2, 0.02, colorectal would be 0.85, kidney would be 0.1, leukemia would be 0.03. So what we can see here is I have selected the top 100 articles from Pubmed, and each went through our code, and it shows us the precision, F1 macro and micro, precision macro and micro, the classification report, and the confusion metrics. So these all go for the top 100, 200, 1000, 2000, and eventually 10,000 articles. So, according to the confusion metric, cancers involving anatomically adjacent organs such as stomach and esophagus, or prostate and bladder, and also liver and colorectal cancers are most easily misclassified. This classifies PubMed abstracts for these cancers as share highly similar biomedical terminology related to anatomy, diagnosis, and treatment. Since TF/IDF based models rely on word frequency rather than semantic understanding, they struggle to distinguish between clinically related cancers. More advanced semantic models such as transformer-based or generative AI models can reduce but not fully eliminate these errors like ever. Maybe in the future though, but like not right now. So next will be our comparison. The slide compares our approach if the instructors provide the framework. The instructor's code uses heavy natural language processing, pre-processing, such as lemmatization and multiple utility modules, which makes it suitable for research experiments but increases complexity and runtime. In contrast, our method uses simpler TF/IDF representation with logistic regression and minimal pre-processing. Despite the simplicity, our model achieves very high accuracy, around 97 to 99%, while training and testing much faster. This shows that lightweight pipeline is sufficient and robust for large-scale PubMed cancer article classification. So if you ever were to work on this later on down the road, first we go at incorporating more advanced NLP models such as BERT or Pubmed BERT for improved semantic understanding, extend classification to multi-label scenarios where articles may belong to multiple cancer types, integrate the model with RIG pipelines to answer researchers use queries using Pubmed literature, and explore features important analysis to identify keyterms and driving prediction. So in conclusion, this project demonstrated the effectiveness of TF/IDF based text representation and logic regression for automatic classification of biomedical literature. This model can assist researchers by reducing manual effort in article categorization, providing quick and reliable predictions for cancer type, offering probability score for uncertainty estimation. This pipeline is memory efficient, reproducible, and can be integrated into larger literature management systems or even retrieval augmented generation frameworks for interactive querying for PubMed data. Thank you for paying attention.